AC measurement. AC measurement is possible with the help of AC meters. You see, when we talk about DC meter, everything is based there on magnetic effect. Magnetic effect is entirely dependent on the direction. But here, the big point of AC is that direction is not fixed, it is always variable. So, magnetic effect is not going to be useful for this. We try to explore another aspect of electricity, that is current, and its heating effect. You see, heating effect is not dependent on direction. If you rub your hands, heat is going to be produced, doesn't matter whether right hand is above or left hand is above. Likewise, heating effect of electricity is also independent of the direction. So, heating effect is utilized in measuring AC, and the instruments are called hot wire instrument. These are also known as hot wire galvanometer. In order to convert galvanometer, obviously we will have to follow the same principle as in the case of DC meter. There we used to take the help of shunt and higher resistances in series. Likewise here also, in order to get meter, you are going to use shunt with galvanometer, and in order to get voltmeter, you are going to use high resistance in series with the galvanometer. But one thing is very peculiar here, that heating effect, or you might say the heat produced, is given by this relation. Here the heat is proportional to square of the current, and heat is going to change the temperature of the wire that we will using here, and this change in temperature is going to change the length of, you see, length will be changed by change in temperature. This is going to depend on heat, and heat is going to depend on square of the current. So, let us precise whole thing. Whatever the deflection is going to take place, that will basically depend on square of the current. So, you can say the deflection is proportional to square of the current, whereas in the case of DC meter, it was direct dependence on current only. That is the basic difference between the two meters, or you can say scale of the two meters. In DC meter, you are going to have the scale of equidistant divisions, whereas here 1 square, this is 1, 2 square, this is 4, 3 square, so 9. That means the distance between two successive divisions is regularly increasing here. That has been clearly demonstrated over here. You see, first, second division, and these divisions are having increasing order of distance, whereas in the case of DC meter, all the divisions are equidistant. Then what is phasor diagram? This also you must know. Phasor diagram, the term phasor itself is composed of two terms, that is phase and vector. Phase and vector, two terms have been combined to find this new term. And what is done over here, we use voltage and current as the vector, and the difference between them, their phase difference, is shown over here. Suppose it's not 90-degree phase difference, it's here. It's clearly shown over here, current, voltage. The phase difference here between the two is phi. It simply means V is V0 sin omega t, and for writing this I0 sin omega t plus phi. You see, always we'll have to proceed anti-clockwise in order to check which one is leading. Here in this case, current is leading. Voltage is lagging behind because you'll proceed anti-clockwise. Now, let us see how power is calculated in AC circuits. In DC, you are already aware, for power, the formula is V into I. Here, through the analogy, you might think VRMS, IRMS, but no, because the power is variable, voltage, current, all are variable, even the phase is also variable. So, we need to calculate the average power, and by taking the average by trigonometrical method we will get this relation. You see, instead of IRMS, you are having IRMS cos phi. That means cos component of the current is effective here. That has been clearly shown over here. This is IRMS. Its cosine component or cos component. This is effective component and responsible for consumption of power. So, cos phi is also known as power factor, whereas this is not going to play any role in power consumption. This is known as wattless component. So, the basic formula is Vrms, Irms, cos phi. If phi is equal to 0, cos phi 1 power is going to be maximum. If phi is 90, as in the case of L or C circuits, we'll see later on, there in that case power is going to be 0. The best example is choke coil. In choke coil, ideally, if there is no resistance, you see, there will be no consumption of power. But if it has a little resistance, some power will definitely be consumed.